Today I want to present my individual project made at Coventry University. The aim of this project is to build an experimental setup to show students how a control circuit works. The chosen control loop is a speed control for a DC motor. On this picture you can see the experimental setup with a DC motor on the left side. In the middle there's a flywheel to slow down the transient response. Otherwise you could just analyze the system by a scope. The transient response would just need 0.1 seconds. On the right side there's an optical encoder to measure the actual motor speed. Other parts are a brake to simulate a load, a display to show the actual values, and an input structure to choose direction, the kind of control, and the speed. The main tasks were to connect the display to the microcontroller to measure the current motor speed, to construct the mechanical setup, to create an input structure to measure the voltage and the current, to limit the input power to enable a change in direction to show that the controller works in both directions, and to program a real-world controller. The communication between display and microcontroller is difficult, but the whole communication protocol is available at atomsofttech.com. So my tasks are to organize the digits with set point, current speed, current direction, current and voltage. One part is to program a translation table between integer numbers used in the microcontroller and char which are sent to the display. The idea of measuring the speed is quite easy, just counting the signals for a certain period of time. The difficulty is that a frequency above 12 kHz can't be analyzed by counting anymore, because the microcontroller is too slowly. I have to deal with frequencies up to 40 kHz. The solution is a frequency divider to choose a division between 2 and 16,000. This has the advantage to prepare a divide measure time by a certain amount of signals speed measurement. To analyze the current direction, a data flip-flop is used which can deal with frequencies up to 40 MHz. Mechanical setup is built at my workshop at home, so there are no turned or milled parts in it. The challenges are to enable to adjust all parts to face the low precision and to reach a high stiffness to get a high resonance frequency. I sorted threaded rods as a Cartesian coordinate system to reach the adjustability, and I start with thick threaded rods which become thinner with the distance to the mounting plate to reach a high resonance frequency. Here you can see the input structure. It starts with push buttons which are connected to the inputs of RS flip-flops. Important are a lot of pull-down resistors to get a defined state after opening the switch again. To control the LED next to the push buttons, signal MOSFETs are necessary because the RS flip-flop can't provide enough current without damage. The 8 input signals are reduced to 4 by further RS flip-flops to reduce the number of microcontroller inputs needed. These are the current and voltage measurement circuits. The current is measured by analyzing the voltage drop occurring at a defined resistor. The voltage applied at the motor is reduced by a voltage divider to reach a voltage lower than 5 volts. First, the signals are filtered due to the PWM frequency of 8 kHz. Then the signals are amplified by differential amplifiers to reach a defined output. This output is filtered again and then connected to the microcontroller ADC converter. Experimental setup has to work with a laboratory voltage source which provides up to 30 volts and 2 amps. The motor has a resistance of 1.6 ohm, what leads to the problem that the maximum current is exceeded easily when the controller calculates a high duty cycle of the PWM signal. This leads to system failure with a high chance. To avoid this problem, a maximum duty cycle which is dependent on the speed of the motor is calculated. Here you can see the limited current during the change in direction. There the motor is accelerated with maximum power all the time. These are the circuits to enable the change in direction. I was thinking about a semiconductor solution, but the source voltage is changing due to the PWM controlled motor supply voltage, so MOSFETs are quite difficult to control. Thus I have chosen a solution based on relays which can be seen here. This is the complete electronic part of the project with frequency divider, the inputs, the measurement circuits, the change in direction relays, the power switching, the connections to the microcontroller, the display and the microcontroller. Now see the system running with set point, actual speed, direction, voltage and current. At the normal speed of 1500 revolutions per minute, you can see that there is no steady state error. One feature is that you can choose different set points in steps of 100. In this case 200, 700, 1500, 2000 and 2500 are chosen to show that the controller works well for every speed. At low speed, the bend shaft has a higher influence because the bending frequency is lower and thus has a higher influence. The next feature is the change in direction. It takes about 3.6 seconds. The calculated fastest response with 30-watt input power is about 3.3 seconds. The last feature is to show the difference between P and PI control. At the moment, P control is switched on with steady state error and a low compensation of loading effects. Now, when I switch on the PI control, you can see that there is no steady state error and the load is compensated quite well, except small overshoots when the load is increased or decreased. You can recognize the higher current and voltage when the load is increased. Now you can see the whole experimental setup working. Switching on, changing on full speed. You can see the green LEDs on the right side. The first switches on at less than 10% control error, the next one at 2%. Now the fast change in direction. Perhaps you can hear the loading effects at P and PI control, the second column of switches. The supply voltage for the electronic components is 5 volt and for the power circuits 15 volt. I hope you enjoyed watching this video.